So the last time we spoke about various features and we were just talking about cardinality restrictions. So with cardinality restrictions, we can define a class with a given number of values for a property. For example, we can define that a person has exactly 2 biological parents. We use subclass here so that we don't infer it in the other direction. For example, horses as well can have 2 biological parents, but we don't infer that they're a person. But if they're a person, we infer that they have exactly two biological parents. We can define max, which would be, for example, a monogamist, as at most 1 current spouse. And we can define min, for example, that a parent has at least 1 child. In this case, we can use equivalence because if something has at least 1 child, then it would be it can be considered to be a parent. So here, let me return. The type of the value doesn't matter. We say it has precisely 2 biological parents, but we don't specify the type of those parents, or we don't specify the type of the spouse, or we don't specify the type of the child. We just say essentially any value will do. So if we turn to qualified cardinality restrictions, it's the same idea, but we only count the values that have a given class. So for example, we might say that a person is equivalent to having 1 biological parent that is a woman, and having 1 biological parent that is a woman, since a woman is a person, implies being a person. So we can use equivalence here, the owl equivalent class. So it only counts members of that class. So the person might have more biological parents, but only has 1 that is a woman. So there are analogous versions of max and min as well. For owl qualified cardinality, we can have owl max qualified cardinality, and we can have owl min qualified cardinality, for example. So these are the final features. So we can maybe have a look and try to remember some of what we saw on Monday. Class equine might be equivalent to the union of which classes? Any ideas? Equine being the kind of term for like horses and zebras and mules and donkeys and asses and all these sorts of horse-like creatures. So precisely that, right? An equine might be the equivalent to the union of zebra, horse, donkey, mule, ass, and so forth, to all these sorts of animals. I'm trying to think of more. Not sure. Okay. What is the difference or relation between complement of and disjoint with? So we saw 2 examples. We saw that lawful is disjoint with mafia boss, and we saw that dead is the complement of alive. So any ideas about what the difference might be? This one's maybe perhaps a bit more tricky. So in this case, what the main difference is that when we say disjoint with, both of them imply that we can't have an instance of both classes. We can't have an instance of dead and alive at the same time. We can't have an instance of lawful and mafia boss. The difference is that complement of creates a partition of all the elements of the universe. Everything is either dead or alive, right? Whereas disjoint with permits a third option. So someone can be lawful, somebody can be a mafia boss, or something can be neither of those things, right? So the disjoint with permits the possibility of neither of those things. Yeah, it's something else, something different. Give an example use of all values from for offspring of equines. So if you have an equine and an equine has offspring, is there something you can say about all of those offspring? You could say that all of those offspring must be equines, right? So it would be tempting to say, for example, that you know all the offspring of a horse are a horse, but as we saw, zebrids are not really horses as such, right? But at the level of equine, it seems relatively safe. Give an example use of owl's some values from for uncle. So essentially the question is, what do uncles have? What can we say that uncles most certainly have? So we could say, in this case, sorry, let me return here briefly and say that when we use the equine and we say that it has all values from equine on property offspring, okay, what we should define is that it's a subclass. Because otherwise, if something doesn't have any offspring, it would be inferred to be equine if we used equivalent class. So in this case, we would say equine subclass of the class of things that have all values from equine on the property offspring. In this case, okay, so give an example use of some values from for uncle. So what do uncles typically have? What do all uncles have? Well, they would have a sibling. Okay, so we could say that's uncle's subclass of some values from sibling, some values from person, or well, we could assume that uncle is a person. Okay, if not, we could say animal or alive or whatever. But on property sibling. Okay, so we can assume that they have a sibling. But in that case, it would be subclass because other things that are not uncles have siblings as well. We could say that an uncle has a niece or a nephew. So again, that would be subclass because also aunts have nieces and nephews. So yeah, I guess that would be it. How might we codify the semantics of a class only child in OWL? So if someone is an only child, what can we say about them? We could say that aside from all the other information we can give about, okay, child we assume to be human, to be a person. We can give all the usual information about humans, that they have human parents and so forth. But specifically for only child, we could say that they have 0 siblings. So that would be essentially a cardinality, exact cardinality constraint. We say that only child has 0 siblings. Is there anything more interesting we could say? We could say maybe some other things like they can't be uncles, they can't be aunts, at least in the biological sense. But that would actually follow if we were to define similar things for this here, to say that an uncle has a sibling, and then we say that here an only child has no siblings, then we would already know that uncles, only children, only childs cannot be uncles, for example. Any questions or doubts? Okay. So it's important to note that for the moment, trying to illustrate just the features with examples. So these are not really definitions. There are more complex entailments that are possible than what I just showed in the slides, right? So the slides are examples. So before, for example, we spoke about how all of these things here would be of type Godfather, right? But if we have this fourth element, what this definition means is that this class consists precisely of these entities here. This defines the class effectively. So now if we define that Vito Young is of type Godfather, what can we conclude? Do we give for example, an inconsistency? Do we infer something? So in this case, you could probably guess by the example, but we assume that in this case, this entity must be the same as one of these. It must correspond to one of these entities, even if the name is different, right? So that gives rise to to these 3 possibilities, right? So Vito Young might be the same as Vito, might be the same as Michael, might be the same as Vincent. might even be the same as all of them, in fact, right? So we know that there's some disjunction, which means an or case. So we know that Vito Young is same as Vito, or Vito Young is the same as Michael, or Vito Young is the same as Vincent. So we will have to think about how to define these features, and that's something we'll talk about in the next class, which is of course very important. So there's no misunderstanding about what these features mean, what consequences they have, and how to do reasoning over them. So the conclusion here is that Vito Young must be the same as Vito or Michael or Vincent. Returning to the zebra or zebroid running example, we saw that we could previously define the first two elements in RDFS, and also this element here, the subclass definition. So if we have a zebroid has exactly one parent as zebra, we see that that's effectively a cardinality constraint, a qualified cardinality constraint. A zebroid has exactly one parent as non-zebra and an equine. This would be an exact cardinality constraint, where the class here is defined using complement and intersection. So it would be the intersection of the complement of zebra and equine. An equine has exactly two parents. This is a non-qualified, just an ordinary cardinality constraint, because we don't really have to specify that the two parents are equines in this case. Two things cannot be related by sire and dam at the same time. This would be a property disjoint with, which we have now. So we can define all of these in order to set up the inference that Zia is a zebroid. This is a rather complex example, but it gives an idea of the power of OWL. Without OWL, we wouldn't be able to define half of the stuff we would need to derive such an inference. So that's essentially the OWL standard. It has some other features that we won't discuss directly, relating to definitions of data types and annotations and so forth, but they're not part of the core of the standard, let's say. So this is the core of the standard that we'll look at the course. In the next couple of classes, we'll talk a little bit more in detail about how OWL can be defined, how we can do reasoning over it, and some of the challenges associated with doing reasoning over OWL. Any questions about the class? Okay. So briefly, with respect to the lab, so we're in lab 4 at the moment. What we would like to do today is to look at some property axioms in OWL. So the lab today won't cover the entire class. So just as a hint, first of all, note that OWL includes the most important features of RDFS. In fact, the first question in the lab will ask something for RDFS that you've seen in the previous lab. And you will cover essentially all of the property axioms up to here, okay? So you shouldn't need to search for solutions after slide 58. So here you should have all the information you need. Of course, there's some important context here as well, but the features you'll be looking for will have been seen on these slides here. Okay. So, and the class is available on the homepage, and the video is available as well. We'll publish the enunciado in a second. So, okay, let me publish the enunciado and we'll have a quick look at it. That's published, okay. So I'm just gonna download it and open it. Okay, so essentially it's quite similar in general to the previous lab. So you will use the same system. We have some default data about Irish mythology, which which Jaime was interested to put a lab together about. So you need to copy and paste the data into the system. The data are also available in the form if you want to copy and paste from there. It might work better than the PDF. So it's essentially a very similar process to last week, except for you need to be sure to choose the OWL reasoner. Again, just to note that OWL includes the main features of RDFS, by which I mean the main range, subclass, subproperty, and some other features. So you can use these terms as well in the OWL reasoner, and it will understand them. So aside from that, one other thing to note is that in this case, we can have some inconsistency. And in fact, one of the questions asked to raise an inconsistency. So in that case, the system, this particular reasoning system, will just add an error message to the graph, which you will see like this. So there will be a blank note. It'll say, this is an error message, and here's the error. And this error here will give details of why there's an inconsistency. So this is specific to this reasoners. Other reasoners have more problems, let's say, with inconsistency. We'll talk about that later. The lab will focus on property axioms, as already mentioned, and effectively the idea is you add some axioms to infer the data. I guess that's it. Yep. So we'll pass to Discord if there's no questions. Okay, so see you in the Discord.